Okay, so last week I published a video criticizing Linus Tech Tips coverage of the Risc-V architecture, CPU, ISAs as a whole, as well as the dev kit that he took a look at. So I got a lot of pushback on that video, kind of saying that I wasn't being fair and that my video wasn't as good as his in terms of production quality. A lot of the criticism I got in that video, I'm not really taking too personally. It was very clear a lot of people didn't watch the full video. A lot of people even admitted that they didn't watch the full video. And honestly, if people were going to watch the whole video, and if they can't come away with it thinking that I had anything valid to say, that's their problem, not mine. And I'm not here to try and convince them. But one of the one comment that I got that actually kind of made me reflect on the video is that they said, turn my conclusion into an inspiration and to make my own video discussing the topic. And I thought that was a fantastic idea. So what I'm going to do today is I'm going to be giving a little introductory primer into CPU ISAs as a whole, and then talking a little bit about Risc-V and providing some resources if you want to go learn more. So I'm basically going to be making the video that I think Linus Tech Tips should have made if they wanted to cover this properly. So with that, I welcome you, and let's get started and watch this this presentation that I put together in terms of talking about CPU ISAs and Risc-V. So let's get started. So I think an important way to start is by talking about what an instruction set is. So a CPU instruction set architecture, or an ISA, is the collection of commands, operations, and protocols that a CPU understands and executes. It's the language that the CPU uses to perform various tasks that will eventually allow it to talk to software in the form of eventually assembly language and then compilers, and then that lets you actually write code. But we have to start with the building blocks, which are the instructions that the CPU can execute. Each of these instructions represents a specific operation that it can perform. So moving your data, performing arithmetic operations on the data, logical operations, the control flow, so like branching and jumping to different parts of a program. These are all things that a CPU has to be able to do. Now, instruction sets vary between architectures. We'll get to this a little bit more later. But x86 and x86-64 are instruction sets that are used in personal computers, like your gaming PC. ARM is very common in the mobile space, and recently Apple has been using it in their, M1, M2, M3 chips. So it depends on the device that you're using. So there's various CPU ISAs for different tasks. And each one has its own set of instructions, registers, address modes, and other features. So I think that's an idea of what an instruction set is, but let's talk about what it's not. An instruction set is not code. There's nowhere on a chip they just type in a bunch of code, and that's what an instruction set is. It's not code. It describes hardware level architecture in terms of the operations that it can perform. So it's describing what the hardware is doing. It's implemented in hardware using a hardware description language, or an HDL, such as Verilog or VHDL. System Verilog is actually one of the common ones they use in industry nowadays. HDLs allow designers to describe the behavior and the structure of digital circuits, including components that constitute a CPU based on the ISA. So things like registers, multiplexers, adders, things like that. And then those things will actually be used to actually build a CPU or an ALU or things like that. But with an HDL, we can actually, like I just said, we can create ALU, control unit, registers, data paths, all this stuff, and we combine it together to make a final chip, or an IP, if you want to use a technical term. And the actions that this chip performs is what is called an ISA. So some common instructions that pretty much all CPUs are going to use, at least in some form: load, store, when talking about memory access; add, subtract for arithmetic; and or XOR, that's bit level operations; jump or branch, depending on which architecture you're talking about, just allowing you to jump to various stages within a program; and then compare, or conditional execute is what that's actually called sometimes. So those are just some of the basic instructions that a CPU is going to need to be able to perform. Depending on what ISA you're looking at, these instructions can actually be called different things, but this is just a general idea of what they're known as. So let's go through a little bit of some examples here. So this picture on the right is basically a CPU pipeline. It looks complicated, but in the grand scheme of things, it's actually a fairly simple CPU pipeline. So you can see we have our control logic. We're actually moving things. We're actually trying to fetch our initial instructions from memory, decoding it, performing all of our control operations, arithmetic operations, and then we're actually writing it to memory. The left side is a little bit more simple. It basically takes all of these wires and it just kind of consolidates it into a more simple, easier to read visualization. So the user at the PC is going to start by fetching an instruction from memory, which will then get decoded. So we break down what our opcode is for whatever instruction we want to perform. Then we take our data, however that's it depends on what CPU you're using, but however that data is encoded, you actually have to decode that so that it can be processed accordingly. Then it goes through the ALU, so whatever arithmetic needs to be performed, the arithmetic logic unit is going to be doing that, and then it actually gets written back to memory after that instruction is completed. Rinse and repeat, that's basically how it works. So it's basically just a simpler version of this. Now I do have a video that I want to show that kind of shows how this is going to be done in terms of code. So I'm not going to be making anything this complicated just because this is an introductory video, but I'll be showing you how, if you want to do this hardware design using an HDL, I'll be showing you basically a general idea of how that's done. It's going to be pretty simple, but this is going to make a lot more sense when you see it in the context of an HDL. So I will move over to that example now. Okay, so as part of my presentation, I wanted to give a little demonstration into how CPU ISAs are actually implemented. So as I told you, the ISA itself is not code. It describes hardware and how that hardware functions in terms of executing instructions. So I want to give you a better idea of how, using a hardware description language in HDL, we can actually implement instructions. We can describe the hardware that's going to execute those instructions. So what I've done here is I've essentially made a little simple CPU module. And I'm using Verilog for this, but you could use whatever you want. You can use System Verilog, use VHDL, it doesn't matter. The concepts are going to be exactly the same. So to start with, we're going to have three inputs here. We're going to have data A, data B, and then our instruction. These are all going to be 8-bit strings of numbers, binary numbers. And then we're going to have one output, which is our data output. All right, so what we do is we read in our two data inputs and then an instruction. Now, based on that instruction, that's going to tell us what we want to do. All right, so the opcode for the instruction we want to do, we're going to just do add for now. Add is a very simple instruction to do in binary. So we're going to define the code for an add as 4 zeros. So we're going to take 4 bits, 4 zeros, and that's going to be our add instruction. Now we're going to store that in a register. Now registers are how we actually store data. That's what holds the data that we're working with. So we're going to have a 4-bit register for our opcode. So that's going to hold the 4 zeros for our add. This isn't really necessary right now, but it's just as best practice. You're going to have a destination register for where you're going to want to store your data. I just made 3 bits long registers so that we can have up to 7 different registers to put data in. But again, it's kind of outside the purview of this demonstration. So don't worry about that. What you should need to know is right now we're defining a register that's 4 bits long called opcode, and what we're going to be doing is that's going to be holding the 4-bit opcode for add, which in this case is 4 zeros. All right, so let's get into the main function. So we're going to have an always block. So at the positive edge of a clock, we're going to trigger our always block. And then what we're going to do is we're going to actually take our instruction. So we take our 4 bits, 4 zeros, and then we read that in from the instruction. So that's 7 to 4. So when you put in your instruction here, the first 4 bits are is what's going to be the instruction that you want to run. So we can just put in 4 zeros, and then we can just do like 4 zeros, and then, I mean, we can have this will be all ones. It doesn't really matter. But that's going to be an example of an instruction that we would use to do an add, right? And then your 2 data inputs can be a combination of bits that you want. It doesn't matter. So this extracting this string of bits is what tells us that we want to do an add. This is telling us where we actually want to store it, but again, that's outside the scope of this demonstration. Don't worry about that. So then we actually want to perform the add operation. We want to add data A and data B. So what we do is we have a case statement, which is basically, it's kind of like a switch statement. You can kind of think of it that way. It's just basically based on what particular input do a series of outputs. So based on opcode, based on this register, which holds our add instruction, we know that this is going to be 4 zeros, so we're going to want to do an add. So this is our operation for adding. Very simple. We take our output bus, our 8-bit data out, and then we're going to assign that to be data A plus data B. So we simply are just adding our 2 inputs right here, and then putting them on the output bus. It's a very simple operation. Now I could do I could have this case statement be other things. So what I could do is, if I wanted to, I could do like a subtract. So I could do that, and then basically I could do just I could do a minus right here, so I could just do a subtraction operation, and then I could just call that add sub, and then what I would have to do is I have a sub operation, right? So what I would need to do is I would have to have a parameter for that, so that the CPU actually knows that we want to do a subtract. So instead of 4 zeros, what I could have is 3 zeros and a 1, and that is a subtraction operation. All right, so there you go. So based on what the first 4 bits of the simple wire are, whether they're 4 zeros or 3 zeros and a 1, I can either do an add or a sub. So there you go. Yeah, and then at the bottom here, this is just a default case for if this input doesn't match any of my operations. It just defaults to all zeros, so that just tells you that something's wrong. So if you have an opcode that doesn't match any of my instructions, then it's just going to zero out. But that's pretty simple introduction into how you would define something like this using HDL code. So what we're essentially doing is we are giving an instruction that we want to perform, either an add or a subtract. We give our data here, and then we're storing that in the instruction into a register. We're storing the result in a destination register, and then we're actually basically creating a control unit, a very simple control unit, that can take the instruction and perform whatever control operation we want. Actually, I guess, you know what? This isn't really a control unit. This is more of an ALU. It's more of an arithmetic unit. I take that back. I guess this is closer to an arithmetic unit if you want to be super technical. But an arithmetic unit is part of a CPU, so I guess that's important. So yeah, that's just a very, very simple demonstration of how you would use an HDL to actually implement instructions. So like I said, the ISA itself is not code, but you use an HDL language like this to describe the hardware, and that hardware is going to execute the instructions that you want. So hopefully this demonstration was pretty informative. Then I'm just showing you how it's done. So let's get back to the presentation. Okay, I hope that example was pretty good for visualizing how this is done using an HDL. Like I said, it's not as complex as what I'm showing you here, but that's basically the building blocks of how it's done. And if you do that and expand on it more, eventually you'll get something like this. So let's continue on. That's a little bit about how ISAs work in a general rule. So let's talk a little bit about how the different types of instruction sets that we can use here. So let's talk about Risc versus CISC. So Risc stands for Reduced Instruction Set Computer. Some examples of Risc architectures are ARM, PowerPC from IBM, which was actually used in the very early iMacs, as well as the Xbox 360, Nintendo GameCube, and Nintendo Wii. which is pretty cool. And then, of course, Risc-V, which is the up-and-comer. Now, RISC architectures focus on smaller, simpler instructions that execute in fewer clock cycles. That's the key there, is it takes fewer clock cycles to complete these operations. Now, a lot of times what that comes down to is the fact that RISC instructions don't have load store operations within them. They use a load store architecture, meaning that arithmetic happens between data that's already stored in registers. So you have to actually explicitly say you want to load and store in order to access memory. Now, compare that to something like CISC, where load and store are actually built into the instructions. So you can actually just give it an instruction and it will handle all of the load store for you. Whereas with RISC, you actually have to do that yourself. So their load and store are their own instructions. They're actually not built into the instructions for a RISC architecture. So that makes them simpler, but it also means that you have to do more of the instructions. CISC, on the other hand, stands for Complex Instruction Set Computer, and probably the most well-known example of this is x86. That's what's used in your desktop PC. That's it's used in a lot of server CPUs. Intel Xeon, AMD EPYC, Ryzen, Core i7, things like that. So that's the one that's been around for a very long time, and Intel and AMD have both worked on it. Now, with CISC, the instructions are more complex and they take more cycles to execute, but the trade-off is that they have additional features built into them, so things like arithmetic and memory access. They also have more dedicated hardware that can handle more dedicated tasks. So, like, for example, I think it was Sandy Bridge that introduced AVX, Advanced Vector Extensions, that can perform more advanced scientific numerical calculations. That was an extension of the x86 instruction set, and it's a very complex set of instructions that you would not find on a RISC chip, at least not in a base RISC instruction set. So to summarize, RISC, you get a faster execution of simpler instructions. For CISC, you have fewer instructions, but they do more each and they take more time to execute. So it's the trade-off. Most modern CPUs use a mix of these because they both have their good and bad. They both try to achieve efficiency in different ways. It's not just necessarily that one is going to be better than the other. It really just depends on the use case. For example, a lot of people say that RISC is inherently better than CISC. Not necessarily the case. There are a few cases where CISC is necessary. So, for example, systems in which your memory accesses are limited, that might be a case where you want to use CISC so you can actually streamline how that memory access takes place. But for scenarios where that's not necessarily a concern, RISC might be better. So it really just depends on what you're doing. And most modern CPUs will use a mix of these because when it comes to very simple instructions, RISC is great. But there are cases where they want to have more robust, more complex instructions for whatever dedicated task they're doing. So, for example, machine learning or GPUs, for example. If they need something that's a little bit more complicated to perform, there are cases where you want more complex instructions, and that's going to be more efficient for a dedicated task than a RISC instruction. So that's we've talked a little bit about what instruction set architectures are in general. And I've given you some demonstrations, some examples of how they're implemented. And then we've talked a little bit about RISC versus CISC. So let's talk about Risc-V. This is the new up-and-coming computer ISA that everyone's very excited about because it's open source. And it's going to... The impact that Risc-V is going to have on the chip design world is great. And I think that it's very important to talk about that. So the big thing about Risc-V is that it's open source based on RISC principles. Now, it's designed to be modular, so basically it's very easy for people to add their own instructions or remove what they want for their own chips. So, for example, if you want to add custom instructions, let's say you have a chip that wants to perform a very specific purpose, like an accelerator chip or a data compression chip or something, and you know that it needs to perform a very, very advanced series of instructions. Well, maybe you don't want to string a bunch of reduced instructions together, and you want to create a few complex instructions that can go on the CPU that it's going to utilize. You can add complex instructions to this. It's open and modular, so people can add or remove what they don't need or what they want to have. That's what's great about it. And it's a very simple ISA, so it makes the development easier. Compiler development's going to be easier for running code on it. And the HDL code, like I showed you for describing the hardware, is going to be simpler as well. So these are all great things. That the idea, the core of it is it's going to be easier for developers to make chips using this ISA because it's so accessible for not just the big companies and not just like new developers, but also startups who are don't want to have to pay for it as well. Because being open source eliminates licensing costs from ARM or Intel/AMD. So you can develop chips for cheaper, so you don't have to pay licensing costs. Like, for example, Apple, they actually have to pay ARM a license in order to use their ISA in their chips. And like I said, this is useful for startups because they don't have to pay, burdensome licensing costs, and they can just use this free ISA that's very simple to use for whatever chip they're making. It's very empowering for especially smaller companies that want to get into the chip design space. And since anyone can use it and it's so flexible, it's ideal for a wide variety of products, big and small companies can use it. So embedded systems, microcontrollers, things like the Raspberry Pi Pico that are so cheap, you can make them even cheaper by using open source instruction sets for it. AI accelerator chips are probably going to be a lot more common in the coming years as AI is getting bigger. People want to train these language models. Not dealing with the overhead of a more general CPU and using a reduced instruction set that you can take out everything you don't want and put in some actually dedicated AI-specific complex instructions to achieve, whatever outcomes you want. That's great for making these accelerator chips. You can make them more efficient and more dedicated for their tasks this way. It's great. GPUs. If you want to make a GPU that can run your own version of whatever kind of code you want to compile on it, and you don't want to just be limited to whatever NVIDIA gives you, this is a great option for that. So if we want to see people who want to make their own GPUs enter the GPU space, Risc-V is going to empower them to do that. And then obviously desktop and server CPUs. The server/data center space I think is very important to talk about because with Risc-V, since it's modular and simpler, it's going to allow you to cut all the bloat out and only implement the instructions that you necessarily need. So what we can actually see is chips that are going to have reduced power budgets compared to traditional x86 server CPUs. So that's going to allow data centers to save on a lot of power costs that way. So that's great in terms of them saving money. It's just this ISA is going to do so much good for so many sectors of the chip design space. It really cannot be understated. So, with that being said, you can actually develop on Risc-V today. I mean, I keep talking about it, this up-and-coming thing, maybe when it gets to the consumer products, but in terms of being a developer, this is already out there. There are many dev kits that already exist. I actually found this one from Sci-Fi. They actually have a couple different options for this, but this is a Risc-V chip that comes on actually it says industry standard micro ATX board, so theoretically you could just put this into an off-the-shelf case if you wanted to. So it uses a quad-core Risc-V chip. You actually get access to DDR5 RAM, gigabit networking, USB 3, and PCI Express. So if you want to develop any kind of add-in cards for Risc-V, you actually do that. It has all the connectivity that you need for development. So a lot of these tools are out there, and I'll have this one linked down in the description below if you want to take a look at it. And what I like about Risc-V is that it has a lot of documentation and resources available for it. So there are many books published on this topic on Amazon that you can buy. A couple people who have actually been at the forefront of Risc-V development have written books on this, of course. And then, of course, I could not go without mentioning the Risc-V GitHub, which actually has the entire Risc-V manual, along with all the specifications and everything, within it. So that's open and available on GitHub. I'm going to leave a link in the description if you want to go take a look. It's all there for you. You can download it and take a look at it. And if you're interested in getting started. So that's going to wrap up my kind of introduction into instruction set architectures and Risc-V. This is, I think, a much better explanation of this topic. Obviously, I didn't go into the entire, IC design flow, of course, and I can't have the time to describe an entire CPU bring up from, RTL code all the way up to final tape out. But I think that this video served as a very good introduction to kind of get your feet wet into this topic, and kind of to further demonstrate why Risc-V is so important and why it's going to be so influential in the market. So I had a lot of people in my last video kind of criticize me for the things that I said about Linus Tech Tips video. Well, this is what I would have done. So I hope that this serves as a pretty informative video. I hope that some people will be able to make use of it, and hopefully you'll learn something that you hadn't before. So I appreciate you for watching. Please leave a like and subscribe if you enjoyed this video, and I will see you next time.